So having left simple notions of control behind, we're going to see what kind of language we would use if we were going to talk about coordination and how we would study it and what we would pay attention to. One of the first things to note is that when we're studying movement, we're in the physical domain. We're looking at physical movement. Bodies are physical things, and your legs are much heavier and stronger than your arms, for example. And this influences movement because the limbs all have mass and inertia and so on. And whether we're talking about jellyfish or bats or worms or us, most locomotion movements, most movements involved in getting around in the world are more or less cyclic. They go through cycles, so your legs go back and forth as you walk, and the wings go up and down, and the jellyfish pulses. So oscillation is what heavy bodies do under gravity anyway. We've been looking at oscillating systems in physics for 400 years. We have very, very good mathematics for studying things which go through cycles. And so we've an awful lot of existing knowledge we can bring to bear, physical knowledge, which we can bring to bear in order to understand how one part of a body might be coordinated with respect to another. And cyclic movement turns out to be so widespread that we can get a long way with this. Now we need then to develop some kind of a language. If something goes through a cycle like this, we need to say where it is in the cycle. And on the left, you see a time series of something which is just oscillating up and down. And on the right, you can see it trace the same thing, tracing out a point in a circle. If you go through a cycle, then we can make the end of the cycle equivalent to the start of the cycle. And then we can use the language of angles to describe where we are. So we have a measure called phase, which says whether you're at the beginning of the cycle, halfway through the cycle, 3/4 of the way through the cycle, or whether you've gone all the way around and are back to the beginning again. Phase is a useful notion here. And when we have one thing oscillating, we may have more than one, and if two things which are oscillating can influence each other, they will exhibit what we call coupling or entrainment. That is, they will become non-independent in a certain way. Here you see two pendulums hanging off a string, so that the motion of one is transmitted gently through the string to the other, and you can see them moving and passing that energy of oscillation backwards and forwards. So we get sometimes very interesting patterns when groups of things which can oscillate together and move together. This notion of entrainment turns out to be central in understanding how the different parts of the body work together. Here's a nice demonstration of entrainment from Loughborough University. So in that video, we saw a lovely and audible example of entrainment. And you, of course, noticed when all the metronomes came together and popped out, as it were, because they fell in synchrony. But you heard something else there as well. After the first time they synchronized, they sort of fell apart again, and they came back, and they fell apart again, and they came back. This is something interesting that happens among oscillators and will be very useful in understanding limb coordination, which is that just because two things become coupled doesn't mean that they are slaves to each other. Each of them still has their own intrinsic tendencies. And so here we saw the autonomy of the individual metronome, as it were, constantly asserting itself against the emerging totalizing order of synchronization. So in this way we can approach both individual autonomy and collective patterning and notice all kinds of ways in which parts can come together to coordinated wholes. And these are some general basic principles. And that's what we're looking for, because we're seeking to ground the study of movement in realistic principles. These are basic concepts which will work whether we're talking about fins or wings or legs. So they have a great deal of generality. And there's been some good basic science done using simple model systems that explore these ideas so that we can further improve our vocabulary, as it were, learn how better to understand these systems of coordinated parts, and find deep, profound regularities underlying a lot of surface variation. One very influential field here is the field of coordination dynamics, founded by an Irishman, Scott Kelso, from Derry. The underlying mathematical model is known as the Hack and Kelso-Bunce model, and it's worth mentioning just to show you how you develop a model system for drawing out these basic principles of coordination. So in this model system, you ask people to wiggle two fingers in synchrony at the same frequency. So my fingers are now wagging at the same frequency. I can do it with my hands just as well. That's the instructions. Same frequency, waggle your two hands or fingers. Now it turns out that there's two ways of doing this, and only two ways of doing this. And you probably wouldn't have guessed that if I hadn't told you, but if you sat down on a bar stool and you started trying to waggle your hands at identical frequencies, you'd find this pattern really easy to do, and you'd find this pattern really easy to do. Now, so there's the first pattern, and we call this the in-phase pattern, phase being where you are in a cycle, because these fingers are at the same point in their cycle at all times. They start in the midline, and they both reach the maximum extension, and they both come back to the midline at the same time. That's one pattern. It's the in-phase pattern. And here's the other one, the anti-phase pattern. When one is starting its cycle at the midline, the other is already halfway through its cycle. And they keep this difference of half a cycle all the time. It's a constant. These are what we call in antiphase. That's a model system, and it allows us to study variation, to what degree people are free to vary these patterns. It also has some interesting properties. If you start off in antiphase and you speed up, if you don't do anything to stop it, at some stage your hands start to flap. They just fall into an in-phase pattern. So there's a time record from an experiment where you can see the antiphase relation at low speeds, and then they switch to an in-phase relation at high speed. This, once more, is something that's going to be interesting, because you know from yourself that if you're walking at different speeds, you can do that over a range of speeds, but there comes a rate at which you have to switch to a run. A run is a different form of coordination, so that rate-induced transitions in the overall organization are going to be of interest to us, because this is very like locomotion. So this little model system has some nice properties. There's two stable modes at the moderate speed, in-phase and antiphase. There's a transition to a single mode at fast rate. They both end up flapping. That you don't transition back as rate is reduced, incidentally, which is different from gaits. So when you are running, if you slow down, there comes a point at which you have to shift back to a walk. So the details are going to vary in each case, but the idea that the whole coordination changes as rate changes, that's a very important aspect of this model system. There are some detailed things you can observe on this system just before you switch from one mode to the other. For example, the system goes a bit crazy and everything gets a little bit uncoordinated. That's quite typical of biological systems. Shortly before moving from one stable state to another stable state, everything has to become a little bit less coordinated before it can settle down again. It's a very deep principle. So this is a useful model for studying coordination. In the next video, we'll go on and see some of the things you can see, mostly with animals, as we study coordination.